Welcome back. I want to try to talk about a new problem that we're starting to face. In our previous videos, we've watched through how we can take a context and have that entail the properties of some claims, and we can even turn these into programs. Each context will change what we can prove. A different context like omega could entail other results, such as we might call q. If this notation is new to you, go back and see the videos on sequent calculus to see what this notation means. And it might be useful to review what a context means to logic as well. But for now, if you just want a quick refresher, just remember that we could think of a sentence in here as belonging to natural numbers, and we could make claims about natural numbers, such as the natural numbers provide the fact that when x is less than or equal to y, that implies x squared is less than or equal to y squared. I'll leave a link for a video on this so you can see why that's proved in the context of natural numbers. Now, the claim we want to talk about today is what happens when we need multiple contexts to come together. It's quite common that you imagine some applications and you make some calls and you solve a bunch of riddles for what can be done in your new logic. Then you would try to interact with a new scientist who has different contexts and wants to solve new problems, and you perceive that together you'll have more power. So what could be the most straightforward way to say putting them together? If you stare at this information and you want P and Q to come out the other end, we can use the AND symbol to indicate what our goal is. We want P and Q. Both techniques should be now part of our program. What would entail that? Well, we can see that there's coming from two different places. Gamma is what entails P, and omega is what entails Q. So we could simply add both of these as premises to the entailment. This would give us a way to talk about both at the same time. Does this actually solve our problem, though? Let's take this a little bit further. You'll recall that when we talked about implication, we studied this implication and proved it. But we immediately went further and found that there was a complication when you moved to other kinds of numbers. If you're talking about natural numbers, that was true. But if we move to integers, you could have negative numbers where, say, -5 is less than -3, and when you square them, -5 becomes 25, and -3 only becomes 9. So you could not imply this. We could call this P. And if that one's P, then this next sentence is the negative of P, or not P. Taken together, we're saying that the natural numbers, together with the integers, entail P and not P. Hold on a minute. When we describe truth in a sequent calculus, we described its negation as well. When you have something that's valid, together with its negation, you lead to falsity. And falsity is something we try to avoid in logic. Shouldn't we be able to talk about natural numbers and integers in the same place? Surely there must be a way to fix this. And if logical entailment isn't doing it, we might need to reach for something bigger. The problem we've just illustrated is a problem with the language we've created. So far, without telling you, we've been working in what's called a first-order logic. It's a type of logic where all we can do is talk about the variables in one single context. Now that we have several contexts, we might want to simplify and say, actually, our variables should be tamed down a bit. Maybe they don't span everything in the context. Maybe they're localized. Maybe some variables only talk about gamma, and other variables only talk about omega. So when we bring gamma and omega together, we can have P and Q both be true at the same time without conflicting, because they're talking about smaller universes. This is what's known as a higher order logic, or a set theory. In this context, we can see what the thing to do is. We should say that these variables, x and y, only belong to this n, to the natural numbers. And these variables, on the other hand, only belong to z. By separating them out, we now realize there's no conflict. What we'll have is that we'll have a proposition which is only about natural numbers. And we'll have a second proposition which is only about integers. When we bring these together, we realize that we don't have P and not P. We have one flavor of P and a different flavor. This means that we no longer have, strictly speaking, a P and its negation. We don't get to falsity. So how do we stop this inconsistency? We simply put guardrails on our variables. We increase the kind of logic we have by going to higher order logic. Now there's a catch with this. When we have first order logic, it's such a straightforward language that we can actually prove it's consistent. It means it leads to correct results. We can conclude everything is true or false and get the right answers. However, when we move to this higher order language, we lose that result. We introduce the idea of uncertainty, places where we really can't even know if something is true or false, places where we have some ambiguity, and it evolves into a set of assumptions, what people call axioms. They start to declare that in the world I want to study, I will make these assumptions. And then you can have arguments about which way is the right way to go. These arguments will never be settled because they are different from one application to another. The key thing is to articulate your arguments so that everyone knows. So there will still be contexts that can't be done simultaneously for more subtle reasons. But what we don't have to do is throw everything out. So in the coming lectures, what we'll be doing is exploring a way to write down how we put variables together with a context through a set theory, or more generally, a type theory. And we'll see that there's multiple ways to do this, both mathematically and computationally. At some point, there's a fork in the road. They diverge into two different natural languages. The mathematics language follows a set theory, which is very powerful at proving theorems, but very difficult to compute. The computational language makes a lot of programs, but isn't as nuanced as what the mathematics can see. We'll see these differences, but it's really a lifetime career to understand all the different uses of it. Until next time. That's how you take care of your chalkboard.